Good afternoon, everyone. We continue where we left off. We were talking about driving inflation with scalar fields. And since there was so much discussion about the idea of the horizon, I thought I should talk about it. And in order to, before I do so, I will introduce a notion of conformal time coordinate. So we have the Friedman metric. Remember, we focus on a kappa equal to 0, spatially flat Friedman universe. So ds squared is minus dt squared plus a square of t dx squared. And I can introduce a square of eta minus d eta squared plus dx squared. So evidently, a of eta d eta is dt, or you can write this as eta equal to integral dt by a of t. Okay? And this, for obvious reasons, is called the conformal time coordinate. All right? Because I presume you recognize this metric in terms of the conformal time coordinate, the Friedman metric, is conformal to the Minkowski line element. And the conformal time proves to be useful, okay, to draw light cones, because the light cones will be at 45 degrees, evidently. ds squared equal to 0 implies, if you take one dimension, dx is equal to plus or minus eta. And therefore, the light trajectories, which in terms of cosmic time is very complicated, are much simpler in terms of the conformal time coordinate. And what essentially happens is as follows. I can state the horizon problem in this following manner. So this picture appeared in my slides in my overview lecture, if you recall. So this is, let us say, the CMB surface, last scattering surface. And this is today, okay, eta naught. And you draw a backward light cone. And this is the Big Bang. Maybe I should draw it slightly closer. It's not quite to scale, right? And you draw a forward light cone. So what you find is that, so, you can account for whatever the evolution of A of eta. I hope you recognize that, whatever the evolution of eta, A of eta, in other words, whether it is lambda dominated, radiation dominated, or whatever it is, the light cones are at 45 degrees. So you see this backward light cone from today until the last scattering surface, which is at redshift of Z decoupling. Remember, I didn't derive it, but indicated it's at, about Z of 1,100 or so. The epoch of equality lies somewhere below this. This is redshift of infinity. This is the Big Bang. And this is one of the spatial coordinates, and this is the time coordinate, conformal time coordinate. Now, I haven't evaluated. I would urge you to evaluate this, okay? Assume that this is matter dominated and this is radiation dominated. Before I come to that, I need to estimate the range of eta, okay? So in radiation domination, A of t is t power half. So what is A of eta? What is A of eta? It is dt by t power half. Therefore, it is t power half, which is eta is t power half. So A is, in terms of eta. Okay? Is that clear? You plug dt by t power half is t power half. Okay? So eta is t power half, A is t power half, so A is eta. Yep. Okay. Matter domination, A of t is t power 2/3. So t power 2/3, if I integrate, I will get t power minus 2 by 3 plus 1. which is t power 1/3. So A is t power 2/3. So A of eta is eta squared. And if I had a matter-dominated universe from Big Bang and radiation-dominated universe from Big Bang to all the way, what is the typical range of eta? Eta equal to 0, if you had radiation-dominated universe at the early stages, eta equal to 0 to corresponds to Big Bang, and eta keeps growing. So this is eta equal to 0. Okay? And what is the horizon? What was referred to as the particle horizon. It's simple. So ds squared is dt squared minus dt squared plus a squared dx, right? Or, I can think of along a radial direction, I can even write it as dr, okay? Dr squared. We are focusing on light, so it's 0, okay? And therefore, what do I have? I have the following. Right? So what do I have? I have dr equal to dt by a. Okay? This is some distance along which light travels is dt by a. The horizon is defined as follows. H of t, okay, is equal to the proper distance, right? This is the co-moving distance, proper time, proper distance, dt by a. And there are some limits involved. Okay, the particle horizon goes from 0 to t. Now we can ask what will be the size of this forward horizon and what will be the size of this backward horizon from, okay? And the manner in which I've drawn, it's clear, this is much smaller, okay? And in fact, you can calculate the h backward, okay? Which corresponds to integrating from t equal to t decoupling to t naught, okay, or eta naught, and this corresponds to t equal to 0 to t decoupling, okay? So you can calculate this t decoupling to t naught. And during this period, you have to assume this is matter domination. I'm leaving this out as an exercise for you to do. It's simple integrals to be done. And then you calculate h forward, which is from 0 to t decoupling. You calculate this ratio, right? What will the ratio involve? Okay, so I hope it's clear. HB, let me write the expressions. I will let you do the integral. T naught, okay? In fact, I can do it quickly, okay? So what is this? This is A decoupling because it is at that AT, okay? Integral dt by A of t during radiation domination, 0 to t decoupling, okay? Now this is forward. This is forward from 0 to t decoupling. And during radiation domination, for want of space, let me squeeze this in here. How will I write? I can write A of t as A decoupling, t by t decoupling power half. Right? Okay. I've just chosen your constant so that A equal to A decoupling and at t equal to 0, there is Big Bang. A is 0. Okay. So what will this be? Okay. This is A decoupling. Integral dt by A decoupling. This goes away. T power half t decoupling. All right. So what is this? This is t decoupling. T power half, if I integral dt by t power half is 2 t power half. So it's equal to 2. This is t decoupling power half, 2 decoupling power half, t decoupling power half is 2 t decoupling. Okay. This is not surprising. There is only one time in the problem, which is t decoupling. And the only way I can construct a length out of it is multiplied by velocity of c. Okay. That's what it is. All right. Now, in this space, I will try to evaluate backward. Okay. So let me write it upstairs. So h forward from 0 to t decoupling is 2t decoupling. H backward, t decoupling to, okay, how did I write? T decoupling to t naught. to use the same notation, is A decoupling, because I'm evaluating at this time dt by A of t, but A of t now is the matter one. Okay, so I can write this as divided by A decoupling, t power 2/3, t decoupling power 2/3, right? From t decoupling to t naught. Okay, and this goes away. So what am I left with? T decoupling power 2/3. Okay, and then what is this? T power minus 2/3 plus 1/3. So it is t power 1/3, right? Okay, so it is t naught power 1/3 minus t decoupling power 1/3. Yeah. Now I need to make estimates of t naught and t decoupling. Okay, you can in principle do that. Okay, I would urge you to go back to the first Friedman equation and write the age of the universe in terms of the cosmological parameters. Okay, and you can do that. All right, think about it. I can clarify this later. So you find that, I presume you know what is t naught. It's billion years, 10 billion years or so. Okay, it's 10 power 10. T decoupling is about 380,000 years, it's 10 power 5. So this is much larger than this. So this is essentially T decoupling power 2/3, T naught power 2/3. So if you calculate this ratio, okay, of the backward light cone, T naught, T decoupling T naught, divided by H forward, which is 0 T decoupling, right? Which is what? T decoupling power 2/3. I hope I haven't made any errors. Divided by 2T decoupling is what? This is, there is a factor of 2/3 I have missed when I integrated, but I'm not going to worry about those factors. Okay, I want to make an order of magnitude estimate. Okay, so I will, so for that reason, I'll miss this 2 as well. So essentially, this is T naught by T decoupling for 1/3. It's like 10 power 5 by 1/3. That's the bottom line. Okay, so in other words, the backward light cone is much, much larger than the forward light cone. And this is a statement of the horizon problem. This is the horizon problem, not the version I stated. Yes, it is related to it, and there are reasons to relate them. Okay, but this is essentially this. When someone says it's a horizon problem, one refers to this. And there was another point I mentioned. Remember, I showed the CMB anisotropies with white patches on it, if you recall. Okay, do you recall the comment I made in relation to that? What did I say was the angular size of that patch? Do you recall? Of the order of 1 degree. So what happens is as follows. If you look at this forward light cone, okay, if you look at that, you have to determine the angle subtended by the forward light cone at the last scattering surface. Again, I leave this as an exercise for you to do. It's a standard exercise in background cosmology. What is that you need to calculate? You need to calculate the angle subtended by this forward light cone, which you already calculated, is 2 times T decoupling, okay, in the CMB sky, for which you need to know something called the angular diameter distance. Check out textbooks and calculate what that is, and that happens to be 1 degree. And however, you find that, you know, even points which are far separated by more than 1 degree have the same CMB temperature. This is a statement of the horizon problem. So we have stated the horizon problem in a couple of different ways. Now, there is one nice way to understand how inflation helps you overcome this horizon problem using this picture I have drawn. And this requires understanding this conformal time coordinate. Okay, that's why I introduced it. Let me explain how that helps. So let's do the following. So you have, what is conformal time? Integral dt by A of t, right? And I erase, here it is. A of eta is eta. This is eta squared. So eta equal to 0 is the Big Bang, okay? Let us consider the case where A of t is t power q, right? This corresponds to q with q less than 1, okay? So, but what will happen to eta when dt by t power q is what happens? It is t power, help me, 1 minus q by 1 minus q. So what happens to eta when q is greater than 1? T turns negative. All right. And Q greater than 1 corresponds to A double dot greater than. So this is what inflation essentially allows you to do. It allows you to make eta negative. Eta equal to 0 is the Big Bang. Eta turns negative. So how much inflation do I need? As much inflation, depending on the A of eta, that A of t that you have, so that the forward light cone is as big as the backward light cone. Let me erase this background. Right? So here, eta is less than 0. And you choose your eta adequately so that, and the eta depends on the A of t. A of t depends on your V of phi. Okay. Anyway, the bottom line is that inflation, A double dot greater than 0, allows eta to be negative. There is another case which we considered. E power ht. A of t was e power ht. Right? And t went from minus infinity to plus infinity. What is eta in this case? This is power law. Okay. And this is d theta. Okay. And eta is what? Integral dt by e power ht. So what is this? Okay. This is minus 1 over hi ai. Sorry, ahi. Is that correct? Yeah. Okay. Or a of eta is minus 1 over hi eta, and eta goes from minus infinity to 0. So if you these are examples which indicate that if you have accelerated expansion, if you have an epoch of inflation, you have a conformal time becomes negative. So you can, your Big Bang is pushed behind in some sense, okay, in conformal time, and you can start at a suitably negative conformal time such that the forward light cone is as big as the backward light cone. So that should clarify various questions that arise in relation to the idea of the horizon. So where do we return with that discussion? Let me return to what was I'll come to you in a minute. What was my goal? What we were discussing when we left off in the last lecture, namely driving inflation with scalar fields. Yes. What happens to the time equals to 0? It back? Yes, yes. So what is happening is the moment you are patching different epochs. You have patching different epochs. Okay. So essentially, there is inflation means the Big Bang occurs at a negative eta. Okay. So I don't need to, that's not a reference that is required. Okay. So that is some time. That's it. Okay. So what it means is that in this picture, you can understand the horizon problem or the resolution of the horizon problem through inflation as the inflation permitting you to make negative eta. It in some sense pushes Big Bang behind in a certain time coordinate, and therefore the forward light cone is at least as big as the backward one. Is that clear? Okay. So now we want to drive inflation, and we saw how, with scalar fields, you can achieve inflation under certain condition. And there was a question, what kind of potential do I work with, etc. We need to answer. In fact, there is a simple exercise that you can do. Let me get my notes out so that I can. Right. So remember the equations we had. We had rho is equal to phi dot squared by 2 plus v, and p equal to phi dot squared by 2 minus v. We considered a canonical scalar field. V is a function of phi. I'm suppressing the phi dependence, etc. And I can write the Friedmann equations now. What do I have? H squared is equal to 8 pi g. Now, it's convenient to introduce this quantity. The Planck mass, or square of the Planck mass, which is 1 over 8 pi g. And what do I have? H squared is equal to MPL squared by 3 into phi dot squared plus V. Okay? Now, you also had another equation, okay? We can do the following. Let's consider H dot. The reason for this will become clear. Yes. Sorry. Yes. Yeah, it's dimensionally incorrect. Yeah, thank you. Now, if I calculate H dot, what will I have? 2H H dot, right? Okay, it's better to do it this way. Just give me a minute, okay? So if I calculate H is what? A dot by A. So what is H dot? It is A double dot by A, and then minus A dot squared by A squared, which is A double dot by A minus H squared. Okay? Now we know what is A double dot by A, right? We had A double dot by A is equal to minus 4 pi G plus times rho plus 3P. Okay? So I'm going to substitute that here. The reasons will become evident in a matter of minutes. Just bear with me. Okay? So what do I have now? H dot is A double dot by A is what? Minus 4 pi G by 3. Rho is phi dot squared by 2 plus V plus 3 is phi dot squared by 2, 3 phi dot squared by 2 minus 3V. Okay? And then minus H squared. Okay? Which is A double dot by A is this. So I have substituted this for this. Okay? Minus 4 by, okay? And then I have minus 8 pi G. No, this should not be 4 pi G by, is that 3? Yes, that's correct. 8 pi G by 3 rho pi dot squared by 2 plus V. Okay? So if I write this, what will happen? If I write a 4, okay, this is 2, 2, okay, 2, 2 goes away, all right? So what do I get? Is equal to minus 4 pi G by 3, right? 3, this is 2 phi dot squared, correct? Minus phi dot squared, okay? Minus 2V plus 2V. I hope I got this right, okay? So there is a, that's right. So this cancels out, okay? So H dot is equal to minus 4 pi G phi dot squared by 3, which is phi dots minus phi dot squared by 2 MPL squared. Is that correct? Is that correct? Yes, 2 MPL squared. So these are the two equations I want. All these follow from the equations. So let me erase all this. So H squared is 1 over 3 MPL squared. The reason for all these exercises will become clear very soon. Okay? I'm just building up the required algebra. H dot is minus phi dot squared by 2 MPL squared. Okay? Now, what I can do is as follows. Notice, I can invert this to write V of phi as what? V of phi as what? Is 3 H squared MPL squared, right? V of phi is 3H squared MPL squared minus phi dot squared. No, I made a mistake. This is phi dot squared by 2. Okay? But phi dot squared by 2 is, I know this, 3H squared MPL squared minus, what is it? Phi dot squared by 2 is, minus phi dot squared by 2 is H dot MPL squared. Right. And now, what do I have? I can write phi dot squared is, if I use that equation, is minus 2h dot MPL squared. Okay, or I can write phi dot equal to, okay, I can write it here itself, minus 2h dot MPL, or if I want phi of t is MPL integral dt root minus 2h dot plus a constant. Okay, all I have done is juggled around these two sets of equations that I had, nothing more. Okay, I haven't done anything more. So what are we obtained? I got, this is just the first Friedman equation. Okay, this just follows from this equation and the first Friedman equation, nothing more. And I've combined them to write this equation. Okay, and have I made a mistake? Yes? Sorry, 2, 2. Have I made a mistake here? But this answer is correct. Okay, this should have been plus, is it? Okay. So let me check that. Oh, minus 8 pi g minus, this should have been plus, is it? Minus, that is correct. Okay, so there is an overall minus sign outside. So this is 2 phi dot squared. This should be plus phi dot squared. Okay, right. And then minus this cancellation is fine. Okay, so there is a 3 here. This goes away. The rest of the final expression is right. Okay, thank you. Okay, so what do we have? And then you have this expression. Now, I considered, for instance, de Sitter and power law inflation, right? Where I knew what was A of t, right? So if I have de Sitter inflation, what happens? Okay, so what are we trying to do? We are trying to construct those A of t that we had from a scalar field potential. That's the goal. Okay, in other words, we are reverse engineering the potential. It happens to be convenient. What is happening is that there is one function A of t that we want, and that is interchanged by one function V of phi. That's all. Okay. In some cases, this happens to be trivial to reverse engineer. Okay. So if you have de Sitter inflation, remember what was this? This is A of t is some constant. Let me call this as A1 as I've done before. EHIT. HI is a constant. Okay. So if HI is a constant, right? So you can convince yourself H is A dot by A is HI. It's a constant in de Sitter inflation. This is driven by a cosmological constant. Okay. What is a cosmological constant? When H dot equal to 0, right? Phi is essentially a constant. This is 0. Okay, phi is a constant. What happens to phi is a constant? Phi dot squared is 0. Okay, and H is a constant, therefore V is a constant. So a constant potential where the field is sitting on top is de Sitter. Okay, it's a cosmological constant. The energy doesn't change. What is the other form of solution we considered for inflation? T power Q, right? Power law. So we would like to know what is the kind of potential that you will have. Okay, A of t is T power Q, right? So here we saw that when Q is greater than 1, A double dot is greater than 0. And what is the range of T that was involved? T went from 0 to infinity. Now, is there some place where A double dot changes sign? Okay, so this valid from 0 to t to infinity. A double dot is what? Let me write this as A1 t power q. It is A1 q minus 1 t power q. Q minus 2. right? Does A double dot change sign? Is always for Q greater than 1, A double dot is positive. What does it imply? What does it imply? It is always accelerating. Does that describe our universe? No. So power law inflation has a problem. Okay, I can construct the potential which will give rise to power law inflation. We will do that quickly. But power law inflation does not have an end to inflation. This used to be called the problem of graceful exit. You're able to achieve inflation, but you have to end inflation as well. So there is no way to end it gracefully. Okay, so that's, so power law inflation is not a viable option. You will see people studying it. In fact, we will study it. It has an academic interest, but it's not a viable model. And so the question we are asking is what? What is the question we are asking? V of phi. So you tell me, how am I going to do that? Okay, so phi is a real scalar, right? So this I have written minus root h dot, minus 2 root 2, minus root of minus 2 h dot. H dot has to be negative. Okay, so what is h? Remember what is h in power law? It's A dot by A, it's just Q by T, right? Q is positive, T is positive. So H dot is minus Q by T squared is indeed negative. So what is phi of T? Integral dt by integral dt by t. It's some logarithm of t, modulo constants. Is that clear? Okay. So phi of t is whatever. I'm not going to worry about constants. Integral dt root of minus 2h dot minus is plus 2q by t squared, which is like 1 over t. This is like log t. Phi goes like log t, right? And I'm just going to, I will let you fix all the constants, etc. Initial condition, it starts at some phi I, if, and you need to add some constants, etc. I will let you do that. Now, what do? I need this, okay? So I need V of t. So what we are doing is, we are reverse engineering the potential, right? Given A of t. So we know phi of t, and if I know A of t, I know h of t, I know h dot of t, I know everything, I know V of t, I can parametrically construct V of phi. That's what we're going to do. Okay? So V of t is what? 3h squared MPL squared that we have already calculated. It is 3 MPL squared, Q squared by T squared plus MPL h dot, which is minus MPL. Okay, I hope. No, MPL squared h dot, MPL squared Q by T squared. So this is proportional to 1 over T squared, okay, which is like proportional to, you have to be careful with the constants, etc. Okay, it's like exponential minus phi by MPL with some overall constant which you need to fix. Okay, is that clear? Yes.
If you consider the de Sitter case where A of t goes like e to the ht, you take A double dot, that is also always positive, right?
There is a problem with that as well. Yes, there is a problem here as well as here. I never said this is a, I had already said that is problematic for various reasons. I will come to that. A cosmological constant doesn't induce perturbations. Okay, we will talk about it later when we discuss scalar perturbations. This already indicated there are other problems as well. Both these do not end inflation. Yeah, okay. So I hope it's clear. You have to fix some constants. You have to fix an overall constant as well. Okay. So what have I indicated? I've indicated how you can juggle around your equations and construct what is the V of phi given A of t. Okay, there are other forms. There is something called intermediate inflation, which is somewhere between t power q and e power ht and so on. And you can check out, you can write that down and check out online, and you should be able to find a paper, classic paper, which discusses the V of phi corresponding to that form of A of t. But this is not quite what we want to do. Often we are given a potential in particle physics. okay, or string theory, and we would like to know whether it will admit inflation, what region of the potential will it lead to inflation, what will be the values of the parameter will lead to inflation, whether inflation will end, where inflation will end, etc. And this is where something called potential slow roll parameters come in. And we need to consider the idea of slow roll inflation. So what do we have? We have these three equations, x squared, okay? Remember, there are always three equations, the two Friedman equations and the energy conservation equation, which is equivalent to the equation of motion for the scalar field here, okay? Now we have used the two Friedman equations. Now instead, we will use the first Friedman equation and the equation of motion for the scalar field. So here it is 1 over 3 MPL squared, phi dot squared by 2 plus V. I'm suppressing that V is dependent on phi. And then you have phi dot plus 3h phi dot plus V phi. Let's see. Okay, these equations are exact, right? But we want to consider slow roll inflation. Just give me a minute, I'll grab my notes. Right. So I have already indicated as to how you want phi dot squared to be less than V if you want to achieve inflation. That's when rho plus 3p is less than 0. And we said that we will often consider the situation where phi dot squared is much, much less than V. Okay. Inflation is indeed guaranteed. This is the first of the slow roll conditions. But if an inflaton is rolling down the potential, you should always think of some potential, right, V of phi, in which an inflaton is rolling down. That's not a well-drawn potential, possibly. You can think of some potential like that, where a field is rolling down, okay? And it's like a particle moving down a potential with a friction term. In slow roll inflation, H is nearly a constant. What do you want? If it starts rolling fast, okay, there is a problem. You will not have inflation, but friction will slow it down. Remember the inflationary attractor that I had. But then you want to ensure that it remains slow for a sufficiently long time, because you want an adequate duration of inflation so that the forward light cone is as big as the backward light cone to overcome the horizon problem. Okay. You can estimate how much that is. I would urge you to estimate. It evidently will depend on the form of A of t. Okay. It will typically be about 60 odd E folds. That's the number you will often hear. Okay. What you want is phi double dot much, much less than 3h phi dot. Why? Because if I have this, okay, if I have this, then, I can ensure that phi dot remains small for a suitably long duration, ensuring adequate duration of inflation. Okay? These are known as the slow roll conditions. Okay? Amazingly, you can, if these two conditions are satisfied, you can integrate these equations very easily, almost trivially. I'll come to that in a little while, okay? But I will construct, using these arguments, what are known as slow roll parameters. In fact, I will construct what are known as potential slow roll parameters. SR stands for slow roll. Right? Okay. So what do you have? In the slow roll limit, what do I have? I have x squared is V by 3 MPL squared. because I'm ignoring this. And I'm ignoring this. So the other one I have is 3h phi dot is minus v subscript phi. Remember, v subscript phi is derivative, okay, of v. So first condition is phi dot squared much, much less than v. This is the first condition. Okay. I can write this as follows. Phi dot is what? V phi. I don't care about factors of 3, okay, right? Okay. So I can take into account 3h squared is much, much less than v. Okay. So what do I have? This implies v phi squared by, okay. So it's better that I avoid these factors of 3. What do I have? H squared v is much, much less than 1. But h squared is, there is a factor of MPL squared I've missed, right? No, this is correct, okay? V phi by h squared v. Let me rewrite this here. Sorry, I have taken the v here. So vy squared, h squared, v. Sorry? No, v subscript phi squared by h whole squared. Am I right? Yeah, okay. Okay. Now if I bring, now h squared is v. H squared is v by MPL squared. Yeah? Okay. So conventionally, this is, this allows me to construct what is known as the first slow roll parameter, epsilon v. It is defined as follows. Okay. I hope you understand. Using the equations of motion, we are trying to understand which region of the potential without ever solving for anything where the slow roll parameters will be small. What does it imply? It implies phi dot squared is small, and I will construct the corresponding condition for this, and it will allow you to determine a range of the potential, or a part of the potential where these conditions will be met. Okay. So let's turn to the other one. Okay, I presume you remember this now. I will erase this. Okay, I needed that potential. I will draw it again. Yeah, just give me 1 minute, please. I'll finish this discussion. 3h phi dot, right? We want this condition. Okay, all right. Now, which implies that, okay, so as h is a constant, okay, what do I have? Three h phi dot, okay, is roughly, okay, right? What do I do? Phi dot, where did this correct? So I obtain this to be minus v phi dot, okay? How did I write that? So I use, okay, phi double dot is minus v phi, that's right. I take another derivative, assume h to be a constant, I get this, v phi dot. Differentiation with respect to time, I don't bother about differentiation with respect to this, okay? So I get 3h phi double dot is v phi double dot, okay? Therefore, phi double dot is minus v phi dot divided by 3h, okay? All right. Now, what do I want? Okay, I've just obtained this condition. So you want phi double dot, right? What is our condition? Phi double dot by 3h phi dot to be much smaller than 1. Okay, so what does this lead to? This is modulus of it, okay? 3 phi v phi dot by 3h, and there is another 3h phi dot, okay? 3 square h squared phi dot squared, that's what I have, all right? Okay, is that no, 3h squared phi dot, and this goes away, all right? But this is nothing but, if I ignore factors of V, this is like minus V phi, right? Divided by h squared is V by MPL squared. Okay, all right. So I'm going to erase all this. So I construct my second slow roll parameter. I hope it's clear. Okay, so I have eta V, V phi. Okay, that's the bottom line. So I have just juggled these equations to arrive at it. Okay, and so these are what are known as the potential slow roll parameters. What it tells me is that given a potential, it immediately tells me the region of the potential where epsilon V and eta V are small, which means I can ignore phi dot squared when compared to V, and 3h phi dot, sorry, phi double dot when I compare to 3h phi dot. And what is usually done is that, okay, I will give you a reason for it. We will say that inflation ends when epsilon V is 1. It breaks the condition. Remember, when phi dot squared is comparable to V, okay, remember this arose from the first condition. Phi dot squared is much less than V, okay? This is the acceleration condition, that it doesn't accelerate too much. That is why it involves the second derivative of the potential, okay? And first derivative of the, and so what you do is that you say that when this is of order 1, what you're saying is that phi dot squared is comparable to V and inflation is terminated. Phi dot squared has to be less than V for inflation to occur, okay? If this is of order 1, which essentially means phi dot squared is comparable, the speed of the scalar field is sufficiently high and inflation ends, okay? And, you need both of them for slow roll to occur. And this has to be of order unity for inflation to end. Is that clear? Okay. So we will consider some simple examples. There was a question, was there? Yeah.
So I have two questions. One is, somewhere you assumed h to be a constant when differentiating this equation.
That is correct.
How is it justified? H is not a constant, right?
Well, what you are thinking is that it is almost a constant. It's slow rolling, and therefore it is almost a constant. The change is small. Okay, it's almost a constant. It's not strictly a constant, but at the level of approximation we are working with, it's good enough. In fact, I would urge you at some point of time, I will indicate how you can do so. Otherwise, I have to put together some problems for you guys. Okay, I will try if time permits. Okay, you can numerically integrate this. I can certainly share a Mathematica code which does it for you, okay? You can integrate it numerically and you will find that the slow roll solution we are going to construct is remarkably accurate. And it stops being a good approximation only close to the end of inflation. During the very early stages, okay, it is a very good approximation. Are there any other? Yes.
So all this effort is just to ensure that inflation lasts for sufficiently long, right?
Inflation occurs, inflation lasts for sufficiently long time, and given a potential to determine where inflation will occur and where inflation will end.
Yes. Now, so we have been dealing with phi dots and phi double dots to make sure that inflation lasts for sufficiently long. But we have not said anything about the initial condition for phi itself. What if I have a very large phi and then let it, even if it fast, but because it is very far away?
That will be answered. Just bear with me. Hopefully that I don't know whether I'll answer it in 15, 20 minutes, but I will answer it. Okay. Yes, that's true. If inflation is ending here and you start very close, inflation will end quickly. So you need, given a potential, you need to start at sufficiently high value of phi in order to achieve enough number of e-folds. And I will tell you how to estimate. Just bear with me.
No, so I am asking a larger question. Can I construct inflationary models where I don't even need these two conditions, but I just take phi to be very large so that it still lasts sufficiently long?
I don't know what it means phi to be large. Large compared to what? Just bear with me. After I discuss some models, you can ask your questions. First, do a brief question. These questions can be answered, or you will get a better idea once I discuss some example. Just bear with me.
So previously we had de Sitter model and power law model, both of which had the problem that it's not ending. Inflation is
These
not
are
ending.
not the only cases
Yeah.
where that may happen. There may
Yeah.
be other cases.
Okay, fine.
Okay.
Now we are finding a solution, a slow roll model where inflation is ending based on these conditions.
So no, let me take it. Let me phrase it in my own
Yeah.
words. Those were simple examples to illustrate how inflation, you can have inflationary solutions, simple inflationary solutions, power law, de Sitter, and so on. And if you try to construct in terms of potential, they pose this challenge where inflation doesn't end.
Okay.
Those were simple examples. So often you are not given a A of t. Yeah, okay, you can construct some A of t and construct your V of phi if you want. Okay. Often in particle physics, that's not what you are given. You are given V of phi, and you are asked whether inflation will occur, where inflation will occur, etc. And that is what we are trying to see.
Okay.
Okay. What we are seeing is that, if we assume slow roll conditions, okay, whether we can solve the equation of motion, that's the one of the thing. And before that, we would like to know, given an inflationary potential, what range of, without having to solve, imagine I'm given an inflationary potential, you're blind to everything. You don't know slow roll parameters, etc. What parameter should I work with in order to achieve inflation? Where should I start when I integrate it numerically, say? Okay, you have a code to integrate, and you just plug in the V of phi, I get my A of t, for instance. Okay, so, and I check where A double dot is greater than 0 and where it ends and so on. What range, what should my phi I be? What should the parameter I should work with with the potential? Okay, what should my phi I dot be? Okay, I being the initial condition, I presume. You recognize. Okay, and so these are non-trivial, right? What I'm trying to give you using these potential slow roll parameters is a way to determine which region of the potential, what values of the parameters where inflation will occur. And, we will using these slow roll approximation, we'll actually integrate them as well, as we will quickly see.
Okay.
Yeah? Okay. Yes, very quickly. Manshi.
In the morning, you have run the log plot, right? In that, from the transition to from inflation to at the end of inflation, it was an abrupt change. So when we are trying
No,
to
we haven't. We will discuss that. We will discuss that. Okay. We will focus on inflation. What happens towards the end of inflation, post-inflation? We will construct that. Okay. There is an epoch of reheating. We will discuss what happens after inflation ends, etc. Just bear with me. We'll focus on the inflationary part. I'm trying to ensure I stick to my schedule in terms of time and trying to focus your attention those parts, and we'll construct all of them piece by piece. I will answer all your questions, but I need time to do so. And I will introduce ideas as we proceed that may clear your answers, clarify your concerns. Anything else very briefly? Okay, let's go ahead and we will apply to some potentials. Okay, so we will construct what are known as large field models first. Okay, all right. And these are, it'll become clear why these are called as large field models. Okay, these potentials have the following form. Some V naught phi by MPL over M is what it is. The term large will become clear to you very soon. So now, what do we need to do now? What do we need to do now? Compute? That's it. Do them for me. What is it? Epsilon V is what? MPL squared by 2. Okay. V phi by V is essentially 1 over, no. What is V phi? It is N, correct? So V phi will be N by N squared by phi squared. Is this correct? Okay. This is right. And what is eta V? Eta V what is the dimension of epsilon V? What is the dimension of V? in h bar equal to c equal to 1 units, it's m power 4. Okay? It's m power 4. I will let you convince yourself, right? And phi has dimensions of m. Of course, MPL has dimensions of m, right? M is energy, right? And length is 1 over m. So is time, right? That's not surprising. 1 over time is energy. Energy is m when c is 1. Okay? And so this is m squared, 1 over phi squared. So epsilon v is dimensionless. MPL squared, this is 1 over phi squared, MPL squared, eta v is dimensionless. These are dimensionless quantities. Okay? So now what is eta v now? You should help me calculate. It is MPL squared n into n minus 1. Is that correct? Right? I should. So let me calculate this here. V naught n by MPL power n phi power n minus 1. Right? V phi is V naught n minus 1 by MPL power n, right, into phi power n minus 2 by V is V naught phi power n MPL power n. Okay, so it is n squared. This is correct. This is V naught phi power n MPL power n. This goes away. V naught goes away. N minus 1 by phi squared. This is what it is. Okay. So what does it imply? What does it imply? You see that epsilon v, eta v, is much, much less than 1 when phi is much, much greater than MPL. Okay. So this is, if you have a potential of this type, which is phi power n, not here, v of phi by MPL, right? The field is rolling down. Epsilon v and eta v are small when phi, this is much, much greater than 1. Is that clear? It is where inflation occurs. The field rolls down the potential, right? And then where does inflation end? Okay, inflation ends when epsilon v is 1. What does it imply? Okay, you have MPL squared divided by 2, n squared phi n squared is 1, or phi end equal to n by root 2 MPL. Okay, if n equal to 2, it's at root 2 MPL. So this is 1, and this is phi 1.732. No, what is root 2? 1.404 MPL. Okay, or root 2 MPL. Okay, this is phi n for n equal to 2. Okay, this is MPL. And you can calculate it for n equal to 4 or other pet potentials that you have. Okay, so now there is one question that remains to be answered. If I want 60, so many e-folds of inflation, where should it start? I will answer that in a matter of minutes. Then, apart from large field models, there is one particular model that I would like to consider. There are something called small field models, as you can imagine. It's called a large field model because, the inflation occurs when phi is much, much greater than MPL. Okay, I presume that answers partly your question. Okay, one of the, I will let you do the exercise for small field models. Okay, and these happen to be potentials of the following form. Just bear with me. V of phi is some V naught, right? Some 1 minus phi by some alpha MPL power Q. Okay, all right. I will let you plot the potentials. I will let you determine where you can assume alpha is of order 1 or maybe a few times 1 of order unity. Okay. Determine where the slow roll parameters will be small, where the inflation will end, etc. I would urge you to do that. I'm just going to discuss a more popular model, which happens to be so-called best fit model, which is called the Sriramkumar model. I hope you recognize you can do this exercise for any model. I'm just discussing the simplest of models. And in fact, we will see when we compare with the data, okay, these large field models are ruled out by the data. Okay, we will understand how. All right. So this is a very popular Sriramkumar model. It's contains only one parameter, which is this overall factor, exponential minus √2/3 pi by ampere whole square. Okay, it's an interesting question to ask, how this potential arises. How did people arrive at this potential? You can ask me later. All right. So what do we need to do? You need to do a lot of algebra. I would urge you to write a simple mathematical code which will calculate this for you. Okay. Calculate epsilon v, calculate eta v. All right. And you calculate what is epsilon v, where does epsilon v equal to 1? Okay. And what you find is that phi end by MPL is √3/2. Okay. Log of 1 plus 2 by √3 is like 0.94 or so. Okay. What's the form of the potential? The reason I'm emphasizing this potential is that this will lead to the best fit to the data, CMB data. And it is one of the earliest models proposed by Sriramkumar. And the potential is evidently of this form. Phi, it's like this, right? Sorry, I should write better. And it goes up, settles down at some value, V naught. Okay, right? And this phi end somewhere here, right? This is, let me pop this phi end by MPL. This is like 0.94. So it slowly rolls down, right? This part of the potential, it always slowly rolls down. And as it comes towards the bottom of the potential, it ends. And you may ask what happens, okay? You can see, how does it go? When it is minus phi, what happens to this? This potential, okay, there is a problem. It can go negative and so on. It's a problem on this side. It goes up when it is plus phi, right? Whole square. Yes, I forgot that. Okay, this becomes negative, but there's a square, so the potential goes up like that. It's not a symmetric potential. Okay, all right. And, we'll see. What is supposed to happen is that after it reaches the bottom of the potential, even in the large field model that I talked about, okay, it's phi power n. As it comes down, after it ends, it oscillates at the bottom of the potential. I mentioned in my overview talk as well. That's when reheating is supposed to happen. We will talk about that later, okay? But this is the form of the potential. But what we need to do, I hope to complete this before I'll take a few more minutes, is construct the slow roll solutions. And it's not very difficult to do, okay? So So what have we done? We given a potential, we know where inflation will occur, where inflation is likely to end, okay? But, we need a solution. What it means is that we need a phi of t, for instance, okay? How do I go about doing this? Well, the simplest way to do is as follows. I integrate something, I define something called E-fold, okay? So what is this? Remember, this is dt, a dot by a, so it is dA by dt 1 over a. So this is log a. And this, as I already mentioned, is what is called as E-fold. Okay, all right. So what do you have as far as the equations are concerned? We have 3h squared MPL squared is V in the slow roll approximation, right? Slow roll inflation is easy to understand. It's a matter of dealing with these equations. And then you have what? 3h phi dot is V subscript phi. But phi dot is what? D phi by dt is d phi by dn, dn by dt. But what is dn by dt is h. So I'll write this as phi subscript n. What is phi subscript n? D phi by dn, differential with respect to the E-fold. So what do you have? This is written as, this leads to 3h squared phi subscript n is V phi. Okay? Have I made a mistake? Minus V phi. Yes. Okay? So what do I have? I have 3h squared phi n divided by 3h squared MPL squared is what? Minus V phi by V. Okay? All right. So what do I need to do now? So I have d phi by dn is MPL minus MPL V phi by V. Right? So I can take V phi by V here, and I can take dn here. So I am left with this integral to be done, nothing more. Okay, let's get that done. And as usual, I'm going to do it for the slow roll inflationary model. I'm sorry, for the large field model, because it's easy. You do for the more messier Sriramkumar model, okay? And I will ask you some questions which will require to calculate some observables and compare with the data next week. So you have a weekend to do that exercise, okay? So what do I have? I have d phi by V phi by V equal to minus MPL times dn. I can integrate this with some n equal to 0 to n, some phi I to phi. Okay, now my V phi, as we saw, is some V naught, large field model, right? V naught phi power n by MPL power n. So V phi by V is what? V naught n phi power n minus 1 by MPL power n, okay? And then divided by V naught phi power n by MPL power n. This is n by phi, okay? So integral d phi by n equal to minus MPL. I hope I haven't made any errors. MPL, okay? N, right? And I can take the n here, some phi I to phi. So what it implies is that phi squared minus phi square of n minus phi squared is equal to minus 2 MPL squared NN, okay? In fact, I should write it the other way around from, what is it? Okay, n equal to 0, where it is phi I. Oh, no, it's phi, okay? Okay, all right. So there it is. That's the answer to the question that was asked. Okay, so what do you have? In the large field models, right? I can write phi square n equal to phi I squared, right? Minus 2 MPL squared N. That's it. Okay, so if you have a quadratic potential, right? So what is happening? It starts with a large value of phi and it keeps coming down as n increases for a given small n. Okay, for a quadratic potential, you need to start at something like 15 or 16 MPL and inflation will end at root 2 MPL. Okay, and you can do that exercise for other potentials as well. Okay, I would urge you to repeat the same exercise for this Sriramkumar model. Remember, this is the Sriramkumar model. Okay, Sriramkumar potential. And I would urge you to determine what is phi of n, all right? And what is the slow roll parameters, epsilon v and eta v as a function of n as well, okay? I would urge you to do these exercises. I hope it's clear now. I have now the answer to your question is, I know what phi I need to start at in order to achieve, say, 60 E-folds of inflation. I'll stop here. I'm now completed, I'm fully behind one lecture now. I will try to make up as I proceed. I was afraid this may happen. I'll proceed. I will try not to speed up. I'll somehow try to cover as much as possible. Questions? Please say that again. No, right? It is just, depends on the model.
Yes,
You
yes.
saw the small field model, right?
Yeah,
I was going to some mu times MPL or some alpha times MPL.
Yeah.
Where inflation ends.
So
if the potential is like that, it'll start here and it'll go like that.
yes. So if still there is, if phi is non-zero even after the end of inflation.
Sorry.
If phi is non-zero even after the end of inflation,
Right.
that means that even in the current epoch we shall have a non-zero value of phi in our.
The story is not complete. This is related to reheating.
Oh, okay. Yeah.
Okay. So the energy in the whatever energy is stored in the phi, we will transfer it elsewhere.
So that.
Okay. So I mean, this is something I narrated earlier in the overview talk. This, I think you have adequate information now to understand what I'm saying. During inflation, we are assuming only the scalar field dominates, nothing else. All the energy density and everything else is subdominant. What did we do? We had we had some radiation domination and matter domination. There was supposed to be Big Bang here, okay? This is your epoch of equality. And we have introduced some inflationary epoch. I haven't even said what scale, what time inflation has to occur. Okay, we need to determine that, okay? And there are upper bounds or when inflation can occur, how early can it occur? We don't have any lower bounds. Well, there are lower bounds which are very low bounds. So when so there is radiation in the universe. Radiation is not going to go away. At the start of this inflationary epoch, this is my inflationary epoch. Let us say there's radiation present, okay? We don't know what happened prior to inflation. In fact, we don't know whether there was a Big Bang. Okay, all right? So we don't know what happened prior to inflation. Let us say there was radiation present, okay? If the radiation was present during expansion, it will go by 1/8. So during inflation, what will happen? It will be reduced. I had told you, I haven't shown, but you can do the exercise to show that the universe has to inflate by a factor of 10^26 to resolve the horizon problem. You have all the information to show that. If it increases by a factor of 10^26, the temperature at the end of inflation will be extremely small, okay? And I will not have a hot Big Bang model thereafter. I will not have a radiation-dominated epoch. But I want the radiation-dominated epoch to ensure, nucleosynthesis take place at low enough temperatures, okay? Otherwise, everything is messed up. So at the end of inflation, I want to restore a radiation-dominated era. Okay, what do? The universe has cooled. I need to reheat the universe. So the picture one has is that after inflation ends, during this period, the inflaton oscillates at the bottom of the potential. And I will set up a simple example where I couple the inflaton to radiation and transfer the energy to radiation. It's not difficult to achieve. That's just a simple model. One has to construct a more realistic model. The radiation is not just radiation. It means, it is actually consists of all the standard model particle fields. I have to transfer the energy, and I answered in response to a question this morning. I have to thermalize it as well. Okay, those are what reheating is supposed to achieve. Yes, Raga. Oh, sorry.
So we obtained this relation phi squared of n equal to phi 1 squared minus something. We could have done an analogous calculation for a given potential if we don't assume slow roll condition, right?
You can integrate it numerically.
Yeah.
But I told you how good an approximation this is. It's an exceptionally good approximation.
Yeah, no, I agree. I say that we can find such an
But if you're going to integrate that, you're first going to, look at this. I haven't assumed any values of the parameters, etc. Okay. It's if you integrate in terms of capital N, if you write a numerical code, then you don't need to specify V naught. You just need to specify phi I.
Yeah.
But a priori, when you're numerically integrating, you don't know what the parameters are. You can't integrate without giving the values of the parameters, initial conditions, etc.
No, so that is my question is related to that. So no matter what I do, this phi 1 is still going to remain in my solution.
Phi I, yes.
Yeah, phi I.
Phi initial.
Phi initial. So I can always choose a phi I such that my 10 to the 23
26 E4,
26.
sorry, scale factor.
Yeah, scale
increases
factor.
by- Yeah.
can be satisfied. Right.
Okay, there can be potentials where that may be difficult. Okay, I can imagine there can be parameter values of certain potentials where it is you can achieve inflation but may not permit adequate duration of inflation. I need to construct models immediately. Okay, small field models. In some cases, it can occur. They because explored a wide range of models. Okay, yeah, there can be models where that problem can arise.
There are
Yeah,
a few
right. Yeah,
questions
sure.
online.
Sure.
Since the next is weekend, we will take all this right now.
Sure.
So first,
I
it
want
is
to make
about,
sure I work enough for my weekend. Okay.
they are asking, could you please be precise about what you mean by large field and small field?
Right. When I mean that, phi is much, much greater than MPL, or phi is much, much smaller than MPL. That's all. Large of values of phi compared to MPL.
Could you please tell again why one takes 5 double dot less than 3H 5 dot, the second slow roll condition?
So phi dot squared being much, much smaller than V ensures inflation. But we don't want to just, ensure inflation. We want to ensure that it lasts sufficiently long as well. And which means essentially the field should not accelerate too much. Otherwise, it will run away and end inflation. If the velocity is very large, okay, it'll accelerate. I'm sorry. If 3H5, phi double dot is large, it will, accelerate fast enough and ensure that inflation ends quickly. Okay. But to make sure that inflation lasts for a sufficiently long time, we want to make sure phi double dot is much smaller than 3H phi dot.
Okay. They have also asked for references for these lectures. If you can provide references.
So I'll create a list and you can send it to the email list that RRI has.
Okay. And lastly, how can we arrive at the forms of the large field and small field inflationary potentials? Are they completely phenomenological?
They are motivated by one or more particle physics arguments. Small field models are the simplest kind of potentials you can deal with. I'm sorry, large field models. Small field models arise in different contexts. And as I mentioned already, R plus R squared is the Sriramkumar model, which arises from a R plus R squared model, is a very special potential.
Okay.
And that has been extended, to something called alpha attractor models of inflation. Time permitting, I will talk about it in due course.
Okay. There are questions from online participants about recording of this lecture and sharing of them.
I presume that
we will take care of
yeah.
that. We will circulate a mail containing the references that you share, as well as what is the provision for later recordings of the links and so on.
Right.
I believe last question from online participants. Please also explain in one step we took H to be constant. I remember somebody pointed out. Could you repeat again?
So it is, in retrospect, one finds that in slow roll inflation, H is almost a constant. In fact, in most of these models, H from the beginning to the end of inflation hardly changes in slow roll inflation, not even changes by 10%. So the H is it is not evident when you make that approximation why H is, you're not assuming H to be changing. But in some sense, remember H dot is minus phi dot squared by 2 MPL squared. You are assuming some phi dot squared is small in some sense, and therefore H dot is negligible, and therefore H is a constant. And it is, as I said already, it is all these assumptions are confirmed by exact numerical calculation. The slow roll approximation is a remarkably good approximation. Are there any further questions here from the audience? All right, let's go have some coffee. Thank you.